not that far back. So this is the original equation that we dealt with. And we said, what are the differences between BIN and BJM? What is the difference? And there is absolutely no difference. They are set up based on whatever the order is in the direction that you're going. So the example that we've been working through was cubic in the U direction, but linear in the V direction. What if it were quadratic in the V direction?
You just follow the same way you've got the other curves.
Right, you still have to set up what is your M choose J, what is your B blending functions, so you still have to compute all of those. But out the right-hand side of that equation, the furthest vector is going to be 1b v squared. What is the transpose going to look like? Well, it'll be 1 minus 2, 1 if we're writing across the rows, 0, 2, 1, 0, 0, 1. What if it were cubic? Well, it would be 1 v squared v cubed. What would that middle transpose look like? 1 minus 3, 3 minus 1, 0, 3, minus 3, 6, 3, 0, 0, 3, minus 3, 0, 0, 0, 1. It's just the transpose of that, okay? So it all depends on what order the surface is in the U, what order the surface is in the V direction. Did that help?
Yes, thank you. Yeah, so V would be the transpose.
What if you're trying to define surfaces that need to be tangent to each other? How do you take two surfaces on your car that you're working on? How do you slide them up next to each other and make them tangent? Well, in our day, we have these dialog boxes that pop up and we start saying, make these things tangent, right? Okay? We do that. But mathematically, what is going on? Well, to get a surface tangent to this surface, we need to basically think about what has to happen across this point. Well, if we know that this line right here represents the tangency going into that point, we need to make sure that it's just extended. We know that this controls the tangency. We need to just extend those out some distance to make sure that tangency is controlled. And the net of these patches control that, okay? So back in my day, when I was doing the wing-to-body fairing on the 757, we had to actually construct the control net graphically. We had to basically build this network out there and then say, this is a point, this is a point, this is a point, this is a point. And so the requirements are you have to share a curve, and these control lines have to be a continuation. And the rest of the surface, you just put it out there. And it will build a patch that is tangent. What if you wanted it to not only be tangent, but you had to have curvature across these patches? Well, what mathematically happens is those lines not only continue, but they have to be the same length. That tangent control net that's constructed out there has to be the same length. And there's other requirements beyond that.
Completely understanding what the difference is between tangency and keeping the curvature.
Okay, so tangency is just a first derivative phenomena. It just says that on tangent, curvature puts this radius of curvature at that point, and it says that the rate of change going left of that point and the rate of change going right of that point is the same. So that's what curvature is controlling across that two-patch area. Tangency doesn't matter. You could have a really short continuation of that line and still be tangent at that point. When light breaks across a surface that is just tangent, it'll flow fairly nicely, and you say, okay, show me the curvature lines across that, and you'll see that it has a severe bend. And looking at the side of an automobile or things like that, you can tell when they don't have the curvature right, because the sunlight breaking across it will have a funny little wow, a funny little bend in that light. So, was there a question?
Well, I was just going to say, isn't it kind of like making it one continuous arc over that point?
It's the rate of change going through that point. So, yeah. So, assume that you're building this truck as the model for going over top of your platform. How would you do that? Well, this you can see has lots of surfaces, okay? In fact, what you do is you don't model the entire vehicle, you model just half of the vehicle and use a mirror technique. And then where possible, you use the largest surface patches that you can. Now this shows that we've kind of trimmed it underneath the hood of the truck, but oftentimes in industry, when they're actually building a surface model, that surface will just continue in there. They won't trim it. Trimming of surfaces can have some pretty ugly effects, okay? If you don't need to trim it, you don't need to join it. If you're just looking for a surface model, oftentimes they won't trim things. But notice that all of these surfaces have to match up and share common lines. Okay? So large surfaces are pretty easily built. This one is trying to talk about how do I fillet this area in here. And the filleting process is painful. It just is. It's a surface modeling thing that's awkward to work with. Another thing that's awkward is how do I build a flare? Well, a flare is nothing more, and you should have seen this kind of in lab, is nothing more than some curves that you've projected out there, and then you build an arc the other direction, and you use those arcs and some curves as kind of the control guidelines to make that surface. I'll pop through just a few of these to give you examples. This is another model, surface model that was built. These last ones are more what we're looking for in your car design. Notice there's not the little bitty features and things like that that we saw in the truck or saw in the car. Let's let General Motors and Ford and those companies take care of the real fine detail. In this class, let's look for big sweeping surfaces, fewer surfaces. There's another kind of example, and the last few, okay? So again, have fun with this, okay? Start out with big sweeping, elegant surfaces before putting lots of detail into it.